Good morning and most welcome to 1288. We will continue the previous lecture of temporal naturalism. We got halfway last time, so I will continue. It is a parallel reading to the Singular Universe, first chapter of Smolin. I was at page 14 and the fourth paragraph here. Can we give truth values to facts apart from those that refer to now? In temporal naturalism, we can give truth values or probabilities to hypotheses about the past. The truth values are objective, but to evaluate them requires evidence available in the present moment. No statement about the future has a present truth value. In timeless naturalism, statements with truth values do not distinguish past, present, or future. For example, in a block universe, interpretation of general relativity, all physical observables are non-local in time. The same is true in moment pluralism. Three, time and laws. The choice between temporal and timeless naturalism has implications that span many of the issues facing modern science and go deep to affect how we conceive of the naturalist project. The most immediate implication is to our concept of a law of nature. To a timeless naturalist, no fundamental law can give a privileged status to the present or refer to the distinction between past, present, and future, as there is no objective distinction between past and future. Any law that is truly fundamental must be timeless and immutable. The Newtonian paradigm. The standard for explanation in physical science is the Newtonian paradigm. It is the formal structure shared by classical mechanics, quantum mechanics, and general relativity, quantum field theory, quantum gravity, and some models of computation. The key to the Newtonian paradigm is the separation of explanation into two parts: laws and initial conditions. Nota bene. To set up a theory in the Newtonian paradigm, we must first specify a subsystem of the universe, which can be plausibly treated to a reasonable approximation as an isolated system and then answer two questions about it. One, sorry. What are the possible states of the system at a fixed time? These states, it is assumed, can be prepared by an experimenter at an initial time or determined by the outcome of a complete measurement at a later time. 2. How do these states change in time? And this is so important, I'm going to make an exception and write it up for your remembrance. This is Newtonian physics in a nutshell. So the first one, what are the possible states of the system at a fixed time. These states, it is assumed, can be prepared by an experimenter at an initial time. Or determined by the outcome of a complete measurement at a later time. Second is, how do these states change in time? It's the trick. This is how you do it. These two questions correspond respectively to what is called the kinematics or dynamics of the system. The answers to these questions must be timeless. That is, not themselves change in time. These answers are coded in the following formal mathematical structures. A space of states P, whose points represent the possible states of the system. That is the results of a preparation or complete measurement. In classical mechanics, this is the phase space. In quantum mechanics, this is the Hilbert space. B, a vector field HA on P or its integral, which is a foliation of P by a family of paths, exactly one of which passes through each point. The Newtonian paradigm joins to this formal structure an experimental practice within which the object that is studied and formally represented is a subsystem of the universe, idealized as an isolated system. the observers remain outside the system, along with clocks used to measure duration and measuring instruments used to determine and in some cases prepare the state of the system. When properly used, this combination of experimental practice and formal representation underlies the dramatic success of physics since Galileo, Kepler, and Newton. The proper use of the Newtonian paradigm. The proper use of the Newtonian paradigm, by which I mean the use that matches up with experimental practice, is to describe records of past observations of isolated systems. One assumes the existence of a system as isolated from the rest of nature except for its interaction with a set of measuring instruments controlled by an observer outside the system. There also must be a clock outside the system. States then correspond to possible preparations or complete measurements as done by an observer using instruments external to the system. Evolution is defined with respect to a clock external to the system. External, very important. To proceed, one makes a series of measurements at times T1, T2, to determine the state of each time. This resulted in a record P2, P2, P1, P2. This record, once made, is static it doesn't change in time. It is therefore entirely appropriate to represent the record by a curve which coincides with the entries in the record at the stated times. This is a mathematical object which is also unchanging in time. The cosmological fallacy. It is, however, fallacious to infer from this that nature is a mathematical object or is really timeless. The reason is that the context of referring to an isolated system, controlled or selected by an external observer, is essential. This dependence on the context of a subsystem of the universe blocks any broad metaphysical conclusions being drawn from the success of the Newtonian paradigm, because any such deduction would require the application of the paradigm to the whole universe. To see why the success of the paradigm is due to its domain of validity being restricted to subsystems, note that there are several aspects to the matching between experimental practice and the formal structure of the Newtonian paradigm. There are many possible trajectories because there are many possible initial conditions that may be chosen by the experimentalist. Thus, two subsystems, otherwise identical in terms of their constituents, the laws they obey, and the boundary conditions and outside influences they are subject to, can have different histories. Furthermore, two histories cannot share any states because there's a unique history through every point P on the state space P. These are far from obvious features of natural systems and show the power of the Newtonian paradigm. Because the isolated system is a small subsystem of the universe, it can be repeated many times with different initial conditions. The experimenter can use their freedom to do the experiment many times to vary the initial conditions, and by doing so test hypotheses as to the laws. So the absolute separation of laws and initial conditions, and thus of laws and states, is tied to the empirical context of studying small subsystems of the universe. The time parameters t in the records and trajectory corresponds to the reading of the clock outside the isolated system. However, and this is a key point, the good fit with an empirical context falls apart if we try to apply this paradigm to the universe as a whole. Reasons for that: unlike the usual case, there's only one system to study, and it happens once. Second, there's only one unique history which is the history of the actual universe. How is that determined? It cannot be selected or imposed by any observer. But a choice of initial conditions for the unique universe must nonetheless somehow be made. How? So there is no rule for the other trajectories which are not chosen. Hence, when one attempts to apply the Newtonian paradigm to the universe as a whole, there's a mismatch. It explains at once too little and too much. It explains too little because it cannot tell us why the one history that is realized in nature is distinguished thusly from the infinity of other trajectories which play no role in nature. It explains too much because it explains an infinitude of potential but unrealized facts about the infinite number of unrealized histories. There is no possibility of choosing or varying the initial conditions, hence of operationally separating the role of laws from that of initial conditions. This makes the application of theories to explain cosmological data different in important methodological ways than the application of theory either to data in the laboratory or in astronomy, where one has many similar systems to study, rather than using the freedom to vary the initial conditions or gather lots of data on similar systems with diverse initial conditions. To test hypotheses as to the laws, cosmologists are required to simultaneously test hypotheses about the laws and hypothesis. About the initial conditions. This leads in some real cases to a problem of underdetermination because it is impossible to separate the role of laws from that of initial conditions in attempts to interpret cosmological data. To ignore this and attempt to scale up the Newtonian paradigm to the universe as a whole is to commit the cosmological fallacy. An important example of the cosmological fallacy and a false deduction from it is the claim that the right interpretation of the equations of classical or quantum cosmology is that the universe is timeless. Classical and quantum models of cosmology appear timeless because they arise from applying to a system with no external clock, a method, and formalism whose empirical context requires an external clock. To deduce from the formalism of classical or quantum general relativity that the universe is timeless is fallacious. the cosmological dilemma. A dilemma arises from the cosmological fallacy, because the Newtonian paradigm, when properly applied to an isolated system in nature, must be seen as an approximation rather than an exact description. This arises because when we regard a subsystem of the universe as an isolated system, we must ignore interactions which certainly are there between degrees of freedom in the isolated system and the degrees of freedom outside of its boundaries. But no subsystem of the universe can be completely isolated. At worst, it is physically impossible to shield a system from the influence of gravitational waves coming from the outside. One is tempted to remedy this problem by expanding the boundaries of the subsystem we regard as isolated, by including more and more in it. But if we try to take this process of enlargements to its necessary limit and include the whole universe in the system, the explanatory context falls apart. Due to the inability to cleanly separate the roles of laws and initial conditions, as I have just discussed, we commit the cosmological fallacy. This is the cosmological dilemma. The only solution to it is to regard any application of the Newtonian paradigm as approximate. Hence, the mathematical precision which the Newtonian paradigm allows must necessarily coexist with an unavoidable limit to the precision with which the predictions of the theory may be compared with experiment. Happily, this coincides with the fact that that theoretical physicists have learned it is best to regard our most successful theories, including QED, the standard model of elementary particles, and general relativity as effective field theories. These describe a truncation of nature gotten by limiting the system to be modeled to a subset of the degrees of freedom of the universe. The question on the table is then, how can we extend physics to a description of the whole universe? The proposal of this essay and the books it summarizes is that this can only be done by embracing the tenets of temporal naturalism. As argued in the books, and as I will expand further below, it is the mostly unconscious reliance on the metaphysical fantasies behind timeless naturalism that is responsible for the current crisis in cosmological theorizing. The answer then to the end of science, threatened by adoption of the multiverse, is to embrace the reality of time and the evolution of laws. For the failure of timeless naturalism in the face of cosmological questions. Timeless naturalism also fails because it renders key questions unanswerable. There are 3 key questions, each crucial for understanding the world on a cosmological timescale. Which no theory couched in the Newtonian paradigm can satisfactorily answer. The first one, why these laws? Two, why these initial conditions? Three, why so the universe so long out of equilibrium? Timeless naturalism also fails because of its inaccuracy in mathematics. The Newtonian paradigm takes the choice of laws and initial conditions as input. Furthermore, there is no evidence that mathematics serves to limit choices of possible theories sufficiently to explain most features of the known laws. This is the case even if one restricts ourselves to unification of the known forces within quantum theory. Hence, it is impossible that the Newtonian paradigm could explain the choice of laws, nor can the Newtonian paradigm offer any answer to the problem of choice of initial conditions. It is not enough to say that the Big Bang is represented in classical general relativity by a solution to general relativity with an initial cosmological singularity, because there are an infinite number of such solutions, and those that correctly describe our universe are quite atypical in the absence of inhomogeneities, and black or white holes in the early universe. Penrose characterized this by the hypothesis that the veil curvature tensor vanishes initially, nor does inflation help, because very stringent conditions on inhomogeneities must be imposed for a solution to inflate significantly. Question 3 is a particular aspect of the initial conditions problem. The question is why our universe is still out of equilibrium, still characterized by strong arrows of time, more than 13 billion years after its origin. As Penrose has argued, part of the answer within the Newtonian paradigm must be that entropy was initially so low that the second law has not yet increased to its maximum. This is necessary because the fundamental laws are believed to be invariant under reversal of the direction of time. So there can be no fundamental distinction between the past and the future. I earlier called the why this problem the landscape problem. Very important. It was much debated. The current crisis in theoretical cosmology can largely be characterized as the failure of the method of explanation based on the Newtonian paradigm to answer these three cosmological questions. The different versions of naturalism offer very distinct responses to this crisis. These follow from their different roles. Each gives to the Newtonian paradigm and consequently to the concept of time on a cosmological scale. First one, timeless naturalism and law. Timeless naturalism makes the following claims as to the nature of laws of nature. The Newtonian paradigm extends to the whole universe. The distinction between states and laws is absolute. Laws are timeless and immutable. The laws of nature are reversible in time because there is no fundamental distinction between past and future. The history of the universe is isomorphic to a mathematical object. This is the usual picture most theoretical physicists believe. But there are costs to committing the cosmological fallacy. The most grave is that no answer is possible to the three questions. Sufficient reason is impossible. In other words, in the words of some commentators, our universe seems preposterous, which is another way of saying that its key features are inexplicable within the governing paradigm of explanation. Temporal naturalism and law. By contrast, a temporal naturalist takes a very different view of the nature of law on a cosmological scale. The Newtonian paradigm applies only to subsystems of the universe idealized as isolated systems. any use of the Newtonian paradigm is approximate and is limited by the degree to which interactions between the system and its complement may be neglected. The Newtonian paradigm cannot be applied to the universe as a whole. Any true fact is a truth about the present or the past. Any verification of a statement's truth value must be based on present evidence. The distinction between laws and states break down. Hence, laws may evolve. The future can be at least partly open. The evolution of laws allows hypotheses with testable consequences to be put forward to answer the first two questions. Two examples are given below, so there is hope for sufficient reason. Laws may be time asymmetric and irreversible. So the third question is accessible as well. 5. Relationalism and its limits. Relational versus intrinsic properties. Relationalism is not just a philosophical position. It is a methodological imperative. Progress in physics can often be made by identifying non-dynamical background structures in the description of a subsystem of the universe and replacing it with a real dynamical physical interaction with degrees of freedom outside of that subsystem. The paradigmatic example of this is Einstein's use of what he called max principle by means of which the role of absolute space in defining the distinction between inertial and accelerated motion in Newton's physics is replaced by the action of the distant stars and galaxies, acting through the dynamical gravitational field of general relativity to influence the selection of local inertial frames. A key step in Einstein's discovery of general relativity was his whole argument, with just H, whole argument, which pointed to the role of active diffeomorphism in wiping out the background structure of the differential manifold, rendering bare manifold points physically meaningless. The result is that space-time is not identified with metric and other fields on a manifold. It is identified with equivalence classes of such fields under diffeomorphism. As already discussed above, in general relativity, physical events are defined relationally and contingently in terms of physical effects perceptible there. The use of diffeomorphisms in general relativity serves as an example of a general method for eliminating background structure, which is to introduce a first kinematical level of description, which is encumbered by background structure, and then to reduce the description to those engendered by inimical system of relation. By defining physical observables to be those invariant under the action of some group acting on that background structure. This is called gorging away the background structure. Three major examples of this are local gauge transformations in Maxwell and Young-Mills theory. Space-time diffeomorphism in general relativity and reparameterizations of the string world sheet in string theory. This may seem like an awkward and indirect way to proceed, but it allows us to write simple local equations of motion for fields. This would be much more difficult once the naive local fields are eliminated, because they are not gauge invariant. Indeed, in all free cases, all the physically meaningful observables are non-local. So I'm a bit scrodgy in my throat. It's winter coming on, cool weather affects. Two relational paths to general relativity, Einstein and shape dynamics. Since important work of Stachel, Julian Barber, and others, the interpretation of general relativity as a relational theory and the key role of space-time diffeomorphism in wiping out background structure are well known and appreciated. But recently there is a new development in the interpretation of general relativity, which is highly relevant for the nature of time, which is shape dynamics. This gives a different way of defining general relativity by gauging away background structure. In the old way developed by Einstein, space is treated on, and space and time, it should be, are treated on an equal footing. Spatial-temporal coordinates provide a background structure which is gauged away by imposing space-time diffeomorphism invariance. Indeed, one of the things that is gauged away in this story is any distinction between space and time, because there are space-time diffeomorphism that will turn any slicing of space-time into a sequence of spaces into any other. This means there is no meaning to simultaneity. Barber has emphasized for years that there is a nagging flaw in the beauty of this story. This resides in the fact that there is a big piece of background structure that is preserved in general relativity, which is an absolute scale for the sizes of objects. We must assume the existence of fixed scales of distance and time, which can be compared with each other across the universe. In general relativity, two clocks traveling different paths through space-time will not stay synchronized, but their sizes will be preserved. So it makes absolute sense to say whether two objects far from each other in space-time are the same size or not. You can gauge away this background structure on top of the space-time diffeomorphism invariance of general relativity, but the result will not be general relativity. The reason is that imposing another gauge invariance changes the number of physical degrees of freedom. But the amazing thing is that you can get to general relativity by trading the relativity of time of that theory for a relativity of spatial scale, so that the number of gauge transformations and hence the counting of physical degrees of freedom are unchanged. The resulting theory is called shape dynamics. Shape dynamics lacks the freedom to change the slicing of space-time into space and time. Consequently, there is a preferred slicing, that is, a preferred choice of time coordinate that has physical meaning. This means that there is now a physical meaning to the simultaneity of distant events. But physics on these fixed slices is invariant under local changes of distance scale. Shape dynamics is not actually a new theory. It is for the most part just a reformulation of general relativity. Its preferred slices are expressible in the language of general relativity, and indeed were already known to specialists of classical general relativity. They are called constant mean curvature, or CMC slices, because certain components of curvature are constant on each slice. The technical statement is that shape dynamics is equivalent to general relativity so long as the space-time has such slices, and most of them do. You might object that these preferred slicings represent a return to Newtonian conception of absolute time, but they do not, because the CMC condition is a dynamical condition so that which slices satisfy it depends on the distribution of matter, energy, and curvature through the universe. Moreover, because the predictions of shape dynamics matches those of general relativity, these preferred slices cannot be detected by any local measurements. The slices nonetheless play a role, which can be seen in how the Einstein equations enjoy an impressive simplification when expressed in terms of them. Shape dynamics, just by its existence, has two important implications for the present argument. First, the impressive empirical success of general relativity cannot be taken as evidence for claims that the universe is fundamentally timeless, or even that there is no preferred simultaneity of distant events. These common claims are nullified by the fact that there is an alternative formulation of general relativity that does feature a preferred simultaneity. Second, the preferred slices of shape dynamics gives us a candidate for a global notion of time needed to provide an objective distinction between past, present, and future, and hence makes temporal naturalism a possible position to hold consistent with current scientific knowledge. Relational purism. A relational purist believes that once background structures are eliminated, physics will be reduced to a description of nature purely in terms of relationships. An important example is the causal set program, which aims to develop a complete theory of quantum gravity and hence nature, on the basis of an ontology of discrete events, the only attributes of which are bare causal relations. These are bare in the sense that event A is a cause of event B is a primitive. The causal set program denies there are any further properties P of A and Q of B such that P of A causes Q of B. The aspiration of the causal set program is to construct the geometry of a Lorentzian spacetime approximately satisfying the Einstein equations as emergent only from a discrete sets of events and their bare causal relations. To date, this has not been realized except in trivial cases where the causal set is constructed by randomly sprinkling Minkowski spacetime with discrete events. Another variety, in pure relationalism, a role for intrinsic properties. This calls for it. Completion of the program of eliminating background structures does not imply that there can be no further properties of events except for their causal and other relations with other events. In an event's ontology, you may eliminate all background structures as the causal set program very nearly does, and still be left with an event having properties which are not specified when you know all the relations with other events. We call such properties intrinsic properties. Intrinsic properties can be dynamical in that they play a role in the laws of motion. For example, in events ontology, energy and momentum can be intrinsic properties of events. They can play a role in dynamics and be transferred by causal links. This view is realized in the energetic causal set framework, according to which momentum and energy are fundamental and intrinsic and defined prior to space-time. Indeed, in this approach, dynamics is formulated strictly in terms of momentum and energy and causal relations. Position in space-time is emergent and comes in first just as Lagrange multipliers to enforce conservation and momentum at events. So another one, dynamical pairings and relational versus intrinsic properties. I would like to argue that it is natural to suppose that energy and momentum are intrinsic in a world in which space and time are relational. This is based on the fact that physics has a particular structure in which space-time variables are paired with the dynamical variables, momentum and energy. This dual pairing is expressed by Poisson brackets and has its most profound implication in Noether's theorem, which says that if there is a symmetry of a physical system under translation in a physical spatial coordinate x, then the corresponding momentum p is conserved. Moreover, in the canonical formalism, p is the generator of translations in x. this can be interpreted to say that if position is absolute and so has symmetries, then the corresponding momentum PA can be defined relationally in terms of translations in X. But note that if space is defined relationally, then there can be no perfect symmetry under translations in space coordinate. The reason is that the identity of indiscernible rules out symmetries, because asymmetry is by definition a transformation from one physical state of a system to a distinct state which has identical physical properties. But Leibniz's principle asserts that no system can have two distinct identical states. So if space is relational, we lose the relational definition of momentum as the generator of translations. So if space is relational, momentum can be intrinsic. We can also turn this around and take the view that momentum is the primary quantity and is intrinsic, and define position relationally as the generator of translations in momentum space. This is the point of view taken by the framework of relative locality. Adding intrinsic momentum and energy variables to the causal set description has an immediate advantage, which is to resolve a long-standing problem with the purist causal set approach, which is to get low-dimensional space-time to emerge from a network of pure causal relations. So I would like to propose that generally we take momentum and energy as intrinsic quantities, defined at a level prior to the introduction or emergence of space-time. Support for this comes from the Einstein equations. The left-hand side is composed of geometric quantities that in general relativity are defined relationally. The right-hand side contains the energy, momentum, the energy momentum tensor, which describes the distribution of energy and momentum on space-time. Ever since Einstein began working on unified field theories, generations of theorists down to the late 20th century string theorists have speculated that progress is to be achieved by reducing the right-hand side to geometry as well, so that physics can be expressed in a purely geometric structure. But perhaps that is mistaken, which would account for its not having worked definitely. Instead, we can posit that is the left side that is emergent from a more fundamental description in which energy and momenta are going from primary qualities, perhaps along with causal relations. 5.5. The uniqueness of fundamental events. For a naturalist, the universe, being the totality of all that exists, must be unique. For a relationalist, this unique universe must contain all of its causes. But a little known consequence of Leibniz's principle of the identity of the indiscernible is that every elementary event must be unique in the sense of being distinguishable from every other event in the history of the universe by its location in the network of relations. It is most straightforward to make this argument with an ontology in which the history of the universe consists of discrete events whose relational properties are fundamentally causal relations. But the argument can be made in other ontologies. These events may, as we have just discussed, also have intrinsic properties, but they have no intrinsic labels. If we want to refer to a particular event, we cannot just give it a name, such as event A. We must give a unique description in terms of its relation to other events that uniquely distinguishes it from all the others. And in that description, you cannot just say event A is the one whose immediate causal past is event B, and C, for B and C must be specified relationally as well. So the description must be based on the past causal set. Going far enough into the past that event A's causal past is distinct from the causal past of any other. So the point is that elementary events are not simply to name, because a complete specification in terms of relational properties must contain enough information to single them out from the vast number of other events in the history of the universe. Given this, let's consider what goes into spelling out the most elementary causal relations, that is, events B and C are the direct causal progenitors of event A, developed in enough detail to relationally describe or address the three events. This is a highly complex statement that carries a vast amount of information. So elementary events are not simple, neither are elementary causal relations. It follows that at the fundamental level, nature cannot be governed precisely by laws that are both general and simple. A complete law of nature would have to explain why event A occurred, which means why the events B and C gave rise to a new event. To give a definite answer to this question would be to pick out which pairs or small sets of events give rise together to new events. As there are vastly more pairs or subsets than that do not have common immediate future events. The question is what makes B and C different from the vast numbers of pairs that do not give rise to new events. Any explanation for this must be based on what makes those common progenitors different from other pairs, i.e., it must involve enough information to pick out by means of their relational properties what makes those that are progenitors distinct from those that are not. So I might stop there. Yes. And I end with a little view of the nature that Smolin and Ungar is defending. Nothing less than the reality of the world. Thank you very much and have a pleasant afternoon. Bye bye.